Hello and welcome. If you want to rotate your curve about the y-axis, you can still use the integral from a to b of 2 pi r ds. The only difference in this case would be that r would be replaced with x. And then if you have x as a function of y, you can, if you're integrating with respect to y, you can replace x with the function it is in terms of y, or if you're integrating with respect to x, you can just leave it as x. In example 2, we are asked to find the area of the surface generated by revolving the curve x equals 1 minus y, where y goes from 0 to 1 about the y-axis. Okay, so let's draw a little picture of what that looks like. He says as he turns the page. Probably should have thought of that before starting the video recording, but now it's too late. Okay, so this curve is the line. This is actually the line y equals 1 minus x. You can also think about this as y equals 1 minus x, which would be a line that has y-intercept of 1 and has a slope of -1. So it goes from 0, 1 to 1, 0. It's tilting so I can draw better. Now that's the curve from y equals 0 to y equals 1. It's just that part of the curve. Now we're going to rotate this about the y-axis. Rotate about the y-axis. So on the other side, you'll end up with a part that looks like that, and we can draw a little bit to make it look a little bit more 3D. Looks like one of those cone hats, right? And it's just the outside part. It's not the filled-in part that we're looking for. Now, if we take a little, if we look at a little piece of the curve and we rotate that about the y-axis, the orbit it makes is something like this. It's a little circular orbit. And the radius of that orbit is given by this horizontal distance, which we can represent as x, right? As x. So this little circle is at a particular y value, but the horizontal distance that represents the radius is given by x. Now here, we have x as a function of y, so if we decide to make our integral in terms of y, we can do that. We can also just make our integral in terms of x. We actually have a choice here. We'll show you in just a minute what your choices are. So the surface area, we can start off, as we always do, the integral of 2 pi r. Well, we've only had one other example, so it's not like we always do it, but we always will be doing this, starting off with the integral of 2 pi r ds. Here, we said r was x, right? R is x, and that's because this r is equal to x is because we're rotating about the y-axis. And then the ds we can replace with, we have our choices. So let's say that we're going to try integrating with respect to y in this case. Okay, let's try doing it that way. So we're going to replace then ds with the square root of 1 plus dx dy squared. Oops. And then with a dy. The reason I'm choosing this is because we have x as a function of y, so we can find the derivative of x with respect to y. And so that would be this form of the ds. It would be the square root of 1 plus dx dy squared dy. So this is going to say that we're going to integrate with respect to y. Again, WTR means with respect to. Nothing that you have to bow to or anything like that. It's just just a saying. All right, so then we have the square root of 1 plus, now dx dy is going to be -1. -1. All right, take the derivative of x with respect to y, you get -1. And so far we're going to integrate with respect to y, but we have this x variable right here. Well, what we can do is just replace that x with 1 minus y. I mean, that's what the x is supposed to represent, is the x values along our curve. And those x values are given by 1 minus y. So we'll have 2 pi times 1 minus y. And we can simplify this radical. This is the square root of 1 plus negative 1 squared, which is the square root of 2. Our limits of integration are y going from 0 to 1. So then if we pull out the 2 pi root 2, we can focus on the antiderivative of 1 minus y, which is y minus y squared over 2. And if you plug 1 in to y minus y squared over 2, you get 0. Then if you plug in 0, sorry, you get 0. You get 1 minus a half, which is a half. Then if you plug in 0 into y minus y squared over 2, you get 0. A half times 2 pi root 2 is just pi root 2. So the area of that cone hat is pi root 2. I wanted to talk about one other way you could set this up. We mentioned that you have a choice about ds. You can choose Nintendo DS or you can choose arc length DS. No. You have a choice about ds, your arc length. So let me write a little on the side, or you could instead use, r is the same thing as x here. It's that horizontal distance, so r is still x. But instead of using the ds that has everything in terms of dy, you can instead write the version where we have 1 plus dy dx squared with a dx at the end. Now, what this would look like is you wouldn't change the x in terms of y. You'd try to write everything in terms of x. Now, in this case, we already wrote that we took the x equals 1 minus y and we solved it for y. So we got y equals 1 minus x. So we already wrote y as a function of x. So now we can find dy dx by just taking the derivative of y with respect to x. Now in this case, you still get negative 1, just like we got before. So we have 1 plus negative 1 squared dx. Now our limits of integration should be in terms of x as well here. So this is going to be x equals whatever the the left side of your arc is at, which is x equals 0, and then all the way to x equals 1. This is like x equals 0 to x equals 1. I'm just writing x equals for emphasis here. And then you could go about and find this square root of 1 plus negative 1 squared, that's the square root of 2. You can bring that out. Find the antiderivative of x squared, or of x, which is x squared over 2, from x equals 0 to x equals 1. And you'll still get the same pi root 2. So this is an alternate way of setting it up. All right, thank you for watching, and see you in the next video.